Hi everyone, our topic today will be eigenvalues and eigenvectors. At the end of the video, you'd be able to define the meaning of eigenvector and eigenvalue. You would also be able to compute all eigenvalues and the corresponding eigenvectors using polynomial method. Let's start. Sometimes when we are multiplying a matrix with a vector, now imagine I have a matrix A here and a vector V. Okay. The multiplication of a 2 by 2 matrix and a 2 by 1 vector would result in a 2 by 1 vector. So let's multiply A and V together. So the first row with vector V, I would have 2 multiplied by 1 plus 2 multiplied by 1, which gives me 4. And now the second row, I would have negative 4 plus 8, which gives me 4. So the result would be another vector. However, this vector could also be written as 4 multiplied by 1, 1, where this vector is actually vector V, right? And so we have AV is equals to a scalar, which I could name as lambda, and vector V multiplied by vector V. Now in this case, vector V is called the eigenvector. Meanwhile, the scalar lambda is defined as the eigenvalue. Now, if we have matrix A and if we have vector V or the eigenvector V, then finding the value of lambda would be quite easy. However, there are instances in engineering or mathematical problems when only the matrix A is given, and our task is then would be to find the values of V and lambda, or the eigenvector and the eigenvalue. And now because there are two unknowns, we would be encountering an obstacle because this is no more linear problem. So this video guides you on finding the possible values of V or the eigenvectors and the possible values of lambda or the eigenvalues using the polynomial method. So let's start. As I've mentioned before, V is the eigenvector and lambda would be the eigenvalue. Now imagine A as a 2 by 2 matrix. For example, 3, 1, 4, 5. And I take V as 0, 0. Then it actually solves this equation. However, the solution V equals to 0, or when all entries are 0, is non-trivial and doesn't produce eigenvalues. And so if AV is equals to lambda V, the vector V or the eigenvector V will never be equals to 0. And also in any case, A, the matrix A, is always a square matrix. It could be 2 by 2, 3 by 3, 4 by 4. Now let's discuss the polynomial method. Now when AV equals to lambda V, A is a matrix and lambda is a scalar. I could now multiply lambda with the identity matrix I, which then gives me a matrix. If you still recall, a 2 by 2 identity matrix would be 1, 0, 0, 1. A 3 by 3 identity matrix would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and now I would have AV minus lambda IV equals to 0. Factor V out, I have A minus lambda I multiplied by V equals to 0. Now, because V can never be 0, the fundamental theorem of linear algebra states that the determinant of A minus lambda I will be equals to 0. And so this is the basis of the polynomial method that we would discuss throughout the video. Now, if you still recall, the eigenvector V will never be 0. However, the eigenvalue lambda may be equals to 0, and we will see this in the next examples. Let's look at a simple problem here. We have matrix A and vectors u and v. Now the question asks, which are the eigenvectors, vector u or vector v? And then we are to calculate the eigenvalues that are attached to the eigenvector. So to determine the eigenvector, remember the formula AV equals to lambda v. So we need to multiply A with vector v or u in this case. So let's multiply A with u. So AU gives us the first row multiplied by vector u. We get 4 plus 4, which is 8. And the second row multiplied by the vector u, we also get 8. Minus 4 times 2 minus 8 plus 8 times 2, 16. So 16 minus 8 is 8. Now, this vector could be rewritten as vector u, which is 4 multiplied by u. So the eigenvector in this case would be vector u. So the eigenvector would be vector u here, and the eigenvalue would be 4. What about the next example? A and vector v. So AV gives us first row multiplied by vector v, you get 2 plus 6, which is 8. And the second row multiplied by vector v gives us negative 4 plus 24, which is 20. Now this new vector could not be rewritten as vector v. So in this case, v is not an eigenvector of matrix A. So there are 3 steps to find the eigenvalues and eigenvectors using the polynomial method. The first step is to solve the characteristic equation the determinant of A minus lambda I equals to 0, which we have discussed earlier, and this would give us the values of lambda or the eigenvalues. And in step number 2, we would then substitute the eigenvalues to find the corresponding eigenvectors or V. And finally, in the third step, we would normalize the eigenvectors. So let's start with the first example. So determine the eigenvalues and corresponding eigenvectors for matrix A. So step number 1 would be to solve the characteristic polynomial A minus lambda I, the determinant of A minus lambda I equals to 0. And so we have here A as 3, 2 minus 4, 9 minus lambda multiplied by I would be lambda multiplied by a 2 by 2 identity matrix, which is 1, 0, 0, 1. So this gives us lambda 0, 0, lambda. So the determinant of this is equals to 0. And now we need to solve for 3 minus lambda. 2 minus 0 is 2. Minus 4 minus 0 is minus 4. And 9 minus lambda would be 9 minus lambda. The determinant is equals to 0. And so we have 3 minus lambda multiplied by 9 minus lambda minus negative 8 equals to 0. So we need to solve for lambda. I will rewrite the equation again. We had 3 minus lambda multiplied by 9 minus lambda plus 8 equals to 0. So let's expand this. 3 multiplied by 9 would be 27. 3 multiplied by minus lambda will be minus 3 lambda. Minus lambda multiplied by 9 minus 9 lambda. Minus lambda multiplied by minus lambda is plus lambda square plus 8 equals to 0. And this could be rewritten as lambda square minus 12 lambda plus 35 equals to 0. And to find lambda, we need to factorize this. So you could use the equation function in your calculator, and we would get lambda minus 7, lambda minus 5. And this gives us lambda as 7 and lambda as 5. So that's the first step. We have lambda equals to 7 and 5. In step number 2, we would substitute the eigenvalues, lambda equals to 7 and 5, to find the corresponding eigenvectors. So let's start this. Remember our original equation, A minus lambda I multiplied by V equals to 0. Now, when lambda is equals to 7, we substitute the values of 7, the identity matrix and matrix A. We have 3, 2 minus 4, 9 minus lambda multiplied by the identity matrix would be 7, 0, 0, 7. Remember, lambda multiplied by the identity matrix 1, 0, 0, 1 gives us 7, 0, 0, 7. So A minus lambda I multiplied by V is equals to 0. So 3 minus 7 would be -4. 2 minus 0 is 2. Minus 4 minus 0 is -4. 9 minus 7 would be 2. So we have this matrix multiplied by V as equals to 0. Remember Gauss elimination when we solved AX equals to B? We had matrix A, we had vector B, and we wanted to solve X. Now we could do the same thing, okay? So we could rewrite this as an augmented matrix, -4, 2, -4, 2, 0, 0. Now we would like to make this be 0. So the new row 2 would be negative of -4 over -4, which is negative row 1 plus row 2. So this gives us -4 to 0. So 4 minus 4 becomes 0. -2 plus 2 becomes 0 and 0. Now we can't really do back substitution because we can't solve for x2. Am I right? So what I would do now is, because the next step is to find x2, I would let x2 be equals to the variable c. Okay, now from the first row, I have -4x1 plus 2x2 or 2c equals to 0. So 4x1 is equals to 2c, x1 equals to c over 2. So the eigenvector would be x1 as c over 2 and x2 as c. And this could be rewritten as c half 1. So we are not done with the eigenvector yet. We will move on to the final step, which is to normalize the eigenvector. And how we do that is very simple. To normalize the eigenvector, we need to ensure that the largest magnitude of all the elements here must be equals to 1. So in order for the largest magnitude for all the elements here to be 1, remember the magnitude is also the absolute value of a number. So in this case, we don't have a problem because there are no negative values. But in case there's a negative value, please take note that the largest magnitude of each element must be 1. And in this case, this is true because the magnitude of half is half, which is less than 1. And the magnitude of 1 is 1, which is 1. And the largest magnitude of the elements in here is 1. By taking CB equals to 1, V would be half and 1. So when lambda is equals to 7, the eigenvector is half 1. If you still remember, there are two values for lambda, which is 7 and 5. And so far, we've only considered for lambda equals to 7. So I would denote lambda 1 as 7. And here we are finding V1. And so far, we have V1 as half and 1. And lambda 1 as 7. Now let's consider when lambda equals to 5. We already have the values of lambda. Lambda 2 equals to 5. And we would like to find V2. So A minus lambda 2i multiplied by V2 equals to 0. And A was 3, 2 minus 4, 9. Lambda 2 multiplied by I, by now you would already know the answer, 5005. Multiplied by V2 equals to 0. And I would like to transform this into the augmented matrix. This would be 0, 0 to find V2. Okay. So 3 minus 5 would be minus 2. 2 minus 0 is 2. Minus 4 minus 0 is minus 4. 9 minus 5 is 4. Okay. And our objective is to make this be 0. So the new row 2 would be negative of negative 4 over 2, which is negative 2, row 1 plus row 2. This gives us minus 2, 2, 0, 4 minus 4, 0, negative 4 plus 4, 0. Alright, and we come across this problem again. Remember the method to solve it. So we are trying to solve for x2. I would let x2 be equals to the variable c. So row 1 would now give me negative 2x1 plus 2. X2 would be c equals to 0. So 2x1 is 2c. x1 would be c. Now V2 would be C and C. Or I could rewrite this as C, 1, 1. And to normalize this, remember the largest magnitude must be 1. So if I let C be 1, V2 now could be 1, 1. So when the eigenvalue is 5, the corresponding eigenvector is vector 1, 1. Let's look at another problem. Now matrix A is a 3 by 3 matrix, and we would be calculating the values of the eigenvalues and the corresponding eigenvectors using the polynomial method. So let's start. The first step is to find lambda, and the determinant of A minus lambda I is equals to 0. So the determinant of A minus lambda I in this case would be lambda multiplied by a 3 by 3 matrix identity, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So lambda multiplied by the identity matrix gives us lambda 0, 0, 0, lambda 0, 0, 0, lambda. A minus lambda I would then be 1 minus lambda. 2 minus 0 would be 2. 1 minus 0 is 1. 0 minus 0 is 0. Then I have 1 minus lambda. and 0 minus 0 is 0. Then I have 1 minus 0 as 1, 3 minus 0 as 3, and 1 minus lambda. So this determinant must be equals to 0, and we are supposed to find the values of lambda. So for a 3 by 3 matrix, we usually have 3 values of lambda. For a 2 by 2 matrix, we usually have 2 values of lambda, like what we had just now. In my opinion, the easiest way to solve this is if I consider the second row. Okay, so this will be positive, negative, positive, negative, positive, negative. So now I don't have to consider the zeros. I only have 1 minus lambda multiplied by the determinant of, so cancelling this and cancelling this, I have 1 minus lambda, 1, 1, 1 minus lambda equals to 0. So now this gives me 1 minus lambda multiplied by 1 minus lambda, the whole thing square, minus 1. This must be equals to 0. I am going to rewrite the equation I had just now. 1 minus lambda multiplied by 1 minus lambda square minus 1 equals to 0. So I have 1 minus lambda equals to 0, lambda equals to 1. I also have 1 minus lambda square minus 1 equals to 0. So when I expand this, I would get 1 minus 2 lambda plus lambda square minus 1 equals to 0. 1 minus 1 is 0. So negative lambda, 2 minus lambda equals to 0. I have lambda equals to 0 and lambda equals to 2. I have now 3 values of lambda. Okay, so lambda 1, lambda 2, and lambda 3. Now, our task is to find V1, V2, and V3. So to find V1, remember A 1 2 1 0 1 0 1 3 1 minus lambda I. So I'm going to start with lambda 1 equals to 1. So lambda I would be 1 0 0 0 1 0 0 0 1 multiplied by V equals to 0. Now I could rewrite this in the form of an augmented matrix. 0 0 0. So I have 1 minus 1 as 0, 2 minus 0 as 2, 1 minus 0 as 1, 0, 1 minus 1 as 0, 0, 1, 3, and 0. So I would rearrange this matrix now to be 1 3 0, 0 2 1, and 0 0 0. Because there are no values for x3, I would let x3 be C. So from the second row, using back substitution, I have 2x2 plus x3, which is c, equals to 0. So x2 would be negative c over 2. And from the first row, I have x1 plus 3x2. x2 is negative c over 2 equals to 0. So x1 would be 3 over 2c. So v1 would be c multiplied by 3 over 2, negative half, and 1. And the last step is to normalize this. Remember, the highest magnitude would be 1, but 3 over 2 is greater than 1. And so what I do is, I take c as 2 over 3 in order to transform 3 over 2 to be 1. And so v1 would be 2 over 3 multiplied by 3 over 2, which is 1. 2 over 3 times negative half is negative 2 over 6. And 1 multiplied by 2 over 3 is 2 over 3. Okay? So when lambda 1 is equals to 1, the corresponding eigenvector would be 1, negative 2 over 6, or negative 1 over 3, and 2 over 3. If you still remember, we had lambda as 1, lambda as 0, and lambda as 2. So we are going to find v2 and v3. So when lambda is equals to 0, lambda 2 multiplied by I would be 0, 0, 0, 0, 0, 0, 0, 0, 0. So A minus lambda 2I multiplied by V2. This would be matrix A, which is 1, 2, 1, 0, 1, 0, and 1, 3, 1. Let's transform the third row. So the new row 3 would be negative row 1 plus row 2. This gives us 1, 2, 1. Row 2 stays the same. And the new row 3 will be 0. Negative 2 plus 3 is 1. Negative 1 plus 1 is 0. And 0. We would now simplify the third row. Okay, we have the new row 3 equals to, I would take negative of a to 3 divided with a to 2, which should be negative 1 multiplied by row 2 plus row 3. Okay, so the first two rows remains the same, 1, 2, 1, 0, 1, 0. Okay, so we simply take the third row minus the second row. 0 minus 0 would be 0, 1 minus 1 would be 0, and the rest would be zeros. Okay, now that our augmented matrix has been simplified, we notice that the third column over here, okay, if I were to draw a staircase, is a free variable, so I let x3 be equals to c, and then from the second row we see that x2 is equals to 0, and from the first row we have x1 plus
2 times x2, x2 is 0, plus x3, and x3 is equals to c equals to 0. Okay, so now I have x1 equals to minus c. We have found v2 from lambda 2 equals to 0. v2 would be x1, x2, and x3, which are minus c, 0, and c. Okay, factorizing c out, I have now minus 1, 0, 1. Notice that the magnitude of each element over here is actually less or equals to 1, and so we let c be equals to 1. We have the second eigenvector as minus 1, 0, 1.
Now when lambda 3 is equals to 2, lambda 3 multiplied by I would be 2, 0, 0, 0, 2, 0, and 0, 0, 2. So A minus lambda 3I would be A is 1, 2, 1, 0, 1, 0, 1, 3, 1 minus 2, 0, 0, 0, 2, 0, 0, 0, 2 multiplied by V equals to 0. So I'm going to rewrite this as an augmented matrix. 1 minus 2 is negative 1. So the new row 3 would be row 1 plus row 3. 2 plus 3 is 5. 1 plus minus 1 is 0. 0.
Simplifying the third row, now we have the new row 3 as equals to negative of a23 over a22, which would be row 2 plus row 3, and we have to copy the first two rows. So 5 times row 2 plus row 3. 5 times 0 is 0 plus 0, 0. 5 times negative 1 is negative 5 plus 5 would give us 0. And the rest of row 3 would also be zeros. Now that I have the simplified augmented matrix, we could see that again, the third column over here contains a free variable. So x3 would be equals to c. Looking at row 2, we have minus x2 equals to 0. Therefore, x2 is equals to 0. From the first row, we have minus x1 plus 2 times x2, which is 0, plus x3, which is c, equals to 0. Therefore, x1 is equals to c. So, our final eigenvector v3 would be x1, x2, x3, which is c0, c, Factoring C out, I have now 1, 0, 1. Since the magnitude of each element is less or equals to 1, we take C to be equals to 1 and V3 would be 1, 0, 1.
We could rewrite the whole thing. Lambda 1 is 1, lambda 2 0, lambda 3 2, V1, V2, V3, 0, 1. So these are our final answers. Okay, class. I know that this topic is a bit difficult, and if you can't get it through the first round of our discussion, try it out again now on your own with your pen and paper and calculator. Right? It's a challenge. This topic is a bit of a challenge, but when you overcome it, it's like when you play a game. The topic would be more interesting to you. Okay, so I'll see you in the next video. Thank you for watching.